Hi again, Holly. Professor Sebastian back, and we're just here wrapping up our feedback for your second exam in calculus. Um, so we're down to question 16. So here we want to assume that all variables are implicit functions of time. So x is a function of another variable t, and y is a function of another variable t. So when you're doing these derivatives, you're not doing dy dx's. You're taking the derivative of each of these with respect to t. So you got to use a chain rule over and over again. So it's 2x, take the derivative of the outside, you've got 2x right, but then you got to take the derivative of x itself, dx dt. Now we don't know what it is, so we just write dx dt. Same thing here, 8y times dy dt, and the same thing here, 4 times dy dt equals the derivative with respect to t of a constant is just 0. So then it becomes you want to solve this for dy dt. It says find dy dt. So solving for dy dt, right? I'm going to factor dy dt out of these two terms to get 8y plus 4. I'm going to bring the minus 2x dx dt to this side, divided by 8y plus 4. And then you plug in these values that you have, and you have it. So be careful here. X and y both are unknown functions of t. So whenever you have a big, a complex function of them, you have to use the chain rule. Okay, so 17. Here we just want to understand, do this derivative, understand that dy is f prime of x dx. So they didn't even make you put those in. You just had to take the derivative of this. So here I have to use a product rule, right? Function times function. So I'm going to write it as x times 1 minus x to the 4th to the 1/2, like you have it. Then you take the derivative. So you're going first times the derivative of the second. So that's 1/2 times 1 minus x to the 4th to minus 1/2. And then times the derivative of the inside, minus 4x cubed. Perfect. But then you forgot the second half of the product rule again. So this was first times the derivative of the second. Then you need second times the derivative of the first. Derivative of x is just 1. So you forgot this term. And then it becomes algebra to simplify it down, which, has some work. So I want you to see that too. Make sure you can simplify this. All right, and then 18. 18 is related rates problem. You just kind of, you had some stuff here, but the bottom line is we have a diameter and we're talking about a circumference and we're talking about an area. So we know the circumference is 2 pi r. Since we're working with diameter, I'm going to write it as pi times d, right? Because the diameter is 2r, 2 of the radius. And then on the next equation, we're talking about area. So area is pi r squared. Well, 2r is d, so d is r over 2. I'm sorry. So r is d over 2, so I plug that in. So I get pi over 4 times d squared is area. So then I understand that the circumference and the diameter and the area are all functions of an unknown, are all functions of t, time. So I now take the derivative with respect to t of both sides of this equation. So I get dc dt, equals pi times dd dt. Now they asked you to solve for dd dt, so you just divide both sides by pi. They told us that the circumference increased, so its rate of change was 2. So this becomes 2 over pi, and then they wanted it as a decimal, so you just put that in your calculator. Then how does the area change? In other words, how does this derivative? So take the derivative with respect to t, dA dt equals 2 pi r dr dt, but we're not doing r, we're doing d. So it's 2 times pi r over 4, so pi over 2 d times dd dt, right here. So then you plug in, so you have pi over 2 and d, so pi over 2 times 18, they're giving you the diameter was 18. And the dd dt we found to be 2 over pi, so you can see that those cancel and you're just left with 18. All right, 19 you had correct, 20. So when you are trying to find the maximum and minimum value, the absolute maximum and minimum value of a function on a closed interval, you check the endpoints and you check any critical points inside the function itself. So you found the critical point to be x equals 0. That means you want to check the function itself at x equals -4, at x equals 3, and at x equals 0. And then the absolute max will be one of those and the absolute min will be one of those. So f of -4 comes out to be 7. This is just a little bit of bad arithmetic here, but it's 7. That's your absolute max. F of 3, the other endpoint, is 0. And f of 0 is -9, so that's your absolute min. Okay, so you seem to kind of know what you're doing. You didn't check the endpoint. You didn't check the critical point that I could see, though. All right, and then on 21, it's a similar problem. Function, closed interval. So we're going to find absolute max and min. So the bottom line is done the same way. So you take your derivative. Now your derivative here can't be 0. The numerator is never 0, so this can't be 0. But the denominator, if it's 0, that means the derivative doesn't exist. And that's also a critical point. So x equals 0 is a critical point. So you have to check h at the two endpoints, -8 and 1, and also at x equals 0 to figure out what's your absolute min and what's your absolute max. Okay? All right, 23, 24, you had correct. I said describe 22 vertically. Let's see. I mean verbally. Let's see what was 22 here. Okay, so yeah, this is the one that walks you through that proof, basically. So we have a function. They want us to show that this function has exactly 1, 0. In other words, crosses the axis only once, the x-axis only once in the interval -1 to 0. The theorem that we're using for that's what's called the intermediate value theorem. The intermediate value theorem says you check the value of the function at one point, you check the value of the function at another point. If it's positive at one and negative at another, it had to cross the x-axis somewhere. So that's what the intermediate value theorem says. So we check the function at the two endpoints, and you have those correct. That means there's at least 1, 0. Now, we wanted to see if there was exactly 1, 0. So how do you find if it's exactly 1, 0? We're going to use Rolle's theorem. Okay, so we take the derivative. Now, the derivative is 4x cubed plus 8. Can that derivative be 0 in the interval -1 to 0? So if you set this equal to 0, you get 4x cubed equals -8. Then you get x cubed equals -2, dividing by 4. So the cube root of -2 is something that's less than -1. So it's not 0 in the interval -1 to 0, no. Which means the conclusion. Okay, so you just need to be able to walk through that appropriately if you get that question again. 23, 24, and then you ran out of time. Gosh, that's a bummer. So I went through these problems for you from 25 on just to make sure you do understand them. So let me just talk about them real quick, even though you didn't get to them, but you do need to understand them as you're studying for the final. So here on 25, we're talked about finding, we're given a function where we're told what the derivative is, and then what are the critical points. So we're told the derivative is that, so we don't need to compute the derivative. That's what the derivative is. So this equals 0 when the numerator is 0, which is that x equals -4, but it also does not exist if the denominator is 0. So in other words, when x is 0. So those are two critical points at -4 and 0. So if you set up your first derivative test with the number line, here's your x-axis. So -4, we know that the derivative is 0, and at 0, the derivative does not exist. Those are critical points. And then we need to see what happens on intervals outside of the critical points. So check a number less than -4, like -5. You see that the derivative is a positive number, so it's positive. So it's always positive over here, which means the function is increasing. From -infinity to -4, the function is increasing. And then let's check a number between -4 and 0. So I checked -1. Plug in -1, 3 over the -1, the fifth root, that's -1. So that's -3, which is negative. So between -4 and 0, the function's the derivative's negative, which means the function is decreasing. So that means we have a local max at x equals 4. All right. I'm sorry, -4. And then I check a number outside of 0, so 1, and we get 5, right? F prime of 1, sorry, is 5. I should say f prime of 1 is 5. So that's positive. So again, the function is increasing. Okay, so it's increasing -1 to -4 and 0 to infinity, decreasing on -4 to 0, which means we have a local max at x equals -4 and a local min at x equals 0. Okay, 26. Here we have a function. We got an interval from -infinity to 3, so it's open on the left side, closed on the right side. We want to identify the extreme values. So when I'm looking at that, I take the derivative, set it equal to 0. I see that x equals 5, 6 is a critical point. So the only critical point from -infinity up to 3 is 5, 6. So I check on the left of 5, 6. So like at 0, I check the derivative. I get to be -5. which is less than 0. So it's always negative over here. It means the function is decreasing from negative infinity up to 5/6. And then beyond 5/6, but before 3, so I'll check at 1. So the derivative is 1, which is positive. That means it's increasing from x equals 5/6 to x equals 3. So that means we have a local minimum at x equals 5/6. Now, since we're including all the way up to x equals 3, that means the function is increasing, and we are including it at 3, so that means there's a local max right here at x equals 3. This is also the absolute minimum then, because it can never be smaller than this, right? If it's decreasing all the way from negative infinity up to x equals 5/6 and then increasing after that, that's the absolute minimum as well. All right, 27. 27 has this problem here where we are given sine of 5x on the interval 0 to 2 pi over 5. So sine of x from 0 to 2 pi covers all of sine function, the whole period. So the period of 5x is 2 pi over 5. So this is what it looks like. It's just that's not 0 to 2 pi. It's 0 to 2 pi. Why does it say over 5 now? It was 11 when I was looking. It was sine of 11x when I was looking at it. Huh. That's really weird. When I was looking at it before, it was sine of 11x, but now it says sine of 5x. Wouldn't change it on the review, I wouldn't think. So I don't know. This should have said sine of 5x, which would be 2 pi over 5 here, which would be pi over 5 here, pi over 10 here, 3 pi over 10 here. Okay, and then you can see you have a local min here, a local max here, another local min here, another local max there. Okay, and then on 28, on 28 you have these. We want to find the extreme points for this function. So y equals x cubed minus 12x plus 4. So we need the derivative. 3x squared minus 3, factor out of 3, then factor x squared minus 1, and you see that minus 1 and 1 are critical points. So again, do your first derivative test. You can see where the local max, the local min are. So these problems are all fairly similar. Then they also want about inflection points. So that's where the function changes concavity. So you take the second derivative, set it equal to 0. You find that x equals 0 is a possible inflection point, but you got to check to the either side of it to see if its second derivative changes, because if it does, it changes from concave down when the second derivative is negative to concave up since the second derivative is positive. So that is a change in concavity, which means that x equals 0 is an inflection point. So the graph would look like this. And then 29. So you're given the first derivative, finding the second derivative is easy right here. You just didn't have time again, you didn't get to it. And then they want you to think about, well, what does the graph of the function look like? So you have to apply your first derivative test and your second derivative test to give an idea of what the graph of the function is going to look like. Okay, and then in 30, we wanted to graph this guy. So basically you want to see where there's holes or asymptotes, right? So I'm going to factor the numerator, factor the denominator. I see that the x plus 2 factors could cancel, which means that when x equals minus 2, I'm going to have a hole in my graph. And then these factors don't cancel, so at x equals 2, I'm going to have an asymptote. So I look for where there's a hole at minus 2 in the graph, and an asymptote at 2, and the only one that could be is B. All right, so that covers exam 2. Tried to give you thorough feedback. If you have any questions, Holly, please don't hesitate to reach out, and let's get you up into that C range as we work up towards the final. Take care. Bye.